Hello, my name is Francisco Peñagaricano. I'm an associate professor at the Department of Animal and Dairy Sciences at the University of Wisconsin-Madison. And today I will be talking about breeding for more sustainable dairy cows. Let me start with a definition of sustainability. This one is a definition that I really like it. It says that the sustainability, it's about meeting the needs of the present without compromising the ability of future generations to meet their own needs. And in a modern view of sustainability, we have three domains, including the economic, the social, and the environment domain. And within each of these domains, we have different challenges, including profit, productivity, cost of production, animal welfare, food safety and workload, and of course, climate impact and water and soil quality. Now, when we think about sustainable dairy farming and we think about our dairy cow, we would like to have high producing dairy cows so we can produce the same amount of milk using less cows. We want to have fertile cows. We do know that fertility has a major impact on dairy farming profitability. We would like to have long-lived, healthy dairy cows so we avoid any problems with the use of pharmacological interventions. And of course, we would like to have high feed efficient cows. We would like to produce the same amount of milk using less feed. Low methane emissions cows, we would like to produce the same amount of milk emitting less methane. And of course, we want to have resilient cows. We want to have cows that exposed to challenges, they maintain production or they bounce back to production very quickly. Today, I will be talking about two of these topics, methane emissions and resilience. Methane represents 11% of total US greenhouse gas emissions, is in fact the second most important greenhouse gas after CO2. And enteric methane accounts for 27% of methane emissions and is in fact the second most important source of methane after natural gas and petroleum. Now, beyond the environmental impact and global warming, we can think of methane as the loss of energy. In fact, it represents 6 to 12% of the gross energy intake, energy that could otherwise be available for production and growth. So there are multiple benefits when we think about reducing methane, including the environment, but also improving production efficiency. When we think about mitigation strategies, there are basically three big mitigation strategies. One is through selective breeding, one is about diet manipulations, and one is about microbiome interventions, right? Methane is produced in the rumen by the methanogens, so maybe if we can manipulate the rumen, we will be able to mitigate methane production. Now, what is key when we think about research on methane is how do we phenotype for methane emissions? And there are multiple ways to do it, from respiration chambers, that is without discussion the gold standard, but very expensive, and probably you can use or measure a few animals, to the using of a laser detector. We have been using the green feed system. We are using green feeds on research farms, as you see here on the left, and commercial farms, as you see here on the right. With our green feed system, for the same cow, we can have many records at different time of the day for multiple days. And we have developed an R package called a green feeder. As you see, we are very funny with our names, and we use this R package to download, process, and report green feed data. The green feed is a system that actually produces a lot of data, and we have developed this R package so the community has a tool to, develop, process, manipulate, and report green feed data, so we can have or we can improve reproducibility in this field. Now, it's very important how you define the trait. Of course, we can have methane production. In fact, the green feed measure grams of methane per day. It's common to see two traits: methane yield as grams of methane per kilogram of dry matter intake, or methane intensity as grams of methane per kilogram of energy corrected milk. These two traits are ratios. Ratios have very poor statistical properties, and we are not using neither of these ratios. But we are using what we call residual methane traits, that there are two. One that we call residual methane intensity, that is methane production adjusted for milk energy and metabolic body weight. So this residual, we call it residual methane intensity. And we have also residual methane yield, that is methane production adjusted for dry matter intake. And we call this residual as residual methane yield. Here I'm showing the variability in methane production. These are 64 cows that we have in the same pen at the same time with the same diet. These are second lactation cows. Second lactation cows produce roughly 400 grams of methane per day, but you see that there are beautiful variation. There are some cows that produce more than 600 grams of methane per day, and we have some cows that produce 300 or less than 300 grams of methane per day. Beautiful variation, and geneticists, we need variation. When we plot residual methane production, we have here in the x-axis is residual methane intensity, methane adjusted for milk energy and metabolic body weight, and here in the y-axis we have residual methane yield, that is methane adjusted for dry matter intake. We have this plot. As you can see, these two residuals are highly correlated. Here we have cows that are producing 150 grams of methane more than what they should in terms of production and body weight, or in terms of intake. And here we have our environmentally friendly cows. These are cows that are producing 100 grams less or 150 grams less of methane than what they should, based on milk production and metabolic body weight or intake. So this is one of our first preliminary results. We estimate heritability using roughly 2,400 Holstein cows in 10 different farms, including research farms and commercial farms. So we have methane production. As you see here, it's a heritable trait with a heritability almost of 30%. Our residual methane trait, residual methane intensity, and residual methane yield are heritable trait with heritability close to 20%. It makes sense that the heritability is lower than methane production because it's a residual trait, but still a quite heritable trait. And then we have residual feed intake. We use it more as a indicator of good performance. It's a trait with heritability around 17%. This is exactly what we were expecting. We estimate the genetic correlation between residual methane intensity and residual methane yield. And as you can see here, these two traits are very highly correlated with correlations of 97%. And then we have the genetic correlation between methane production, the residual methane trait, and this is probably one of the most important results that we have so far. Methane production is positively correlated with residual feed intake. That means that cows that they have a genetic ability to produce more methane, they have the genetic ability to have positive RFI. That means they are less feed efficient. Or in other words, cows that have a genetic ability to be more feed efficiency tend to produce less methane. Those are great news because we have these two sustainable traits, feed efficiency and methane production, that they are correlated in in the same direction. This is a picture of our current efforts in this field of methane emissions. We are working on genomic solutions. We are developing genetic evaluations for residual methane trait, and we plan to update our current selection indices and include those methane traits. We are also working on some management solutions based on milk spectra. Basically, we are working on predicting methane emissions using milk spectra data. I told you before, it's possible to mitigate methane emissions using diet interventions. In terms of nutrition, we are basically working on potential genotype by diet interactions. We are comparing cow emissions versus manure emissions. We want to know if the cows that produce less methane, if the manure of those cows also produce less methane or not. And we are working on diet digestibility. We want to make sure that we select cows to produce less methane. We will not be impacting the ability of those cows to digest diet. And at the end of the day, you know, methane is produced in the rumen by the methanogens. So we are also investigating the composition and activity of the rumen with different methane emission profiles. And we are also investigating two other microbiomes, the oral microbiome and the fecal microbiome, as proxy trait for methane emissions. The second trait that I told you I will present today is resilience. It's this idea of advancing despite adversity. I like this definition of the resilience as the capacity to maintain performance or bounce back to normal functioning after a perturbation. And we started to work, or our first attempt to work with resilience was through consistency. Actually, we investigate consistency of dry matter intake as an indicator of resilience. Here you have two cows, cow A and cow B. These cows are exactly in the same place, same research farm with the same diet. And we measure intake during 45 days. And as you can see here, cow A is a very consistent cow. She always eats roughly 25 kilos of dry matter intake. And her friend, cow B, again, is in the same pen at the same time, under the same diet. As you can see, she is very inconsistent. She eats sometimes 25 kilos of dry matter intake, next day 35, then is back on 25, again 35, then low to 30. So she is all over the place. So we basically investigate this consistency of dry matter intake, and we found that dry matter intake consistency is heritable, with heritability around 15%. We found that consistency of dry matter intake and consistency of milk production are correlated, with correlations around 50-60%. That means cows that tend to be more inconsistent in terms of intake, they also tend to be less consistent for milk production. We found that dry matter intake consistency and residual feed intake are correlated. That means cows that are more inconsistent tend to be positive residual feed intake. That means tend to be less feed efficient. In other words, cows that are more consistent tend to be more feed efficient. And we also found that dry matter intake consistency is correlated with fertility. We also work with consistency of milk production as an indicator of resilience. Again, we have two cows in the same farm, the same time in the same pen. We have cow A is very consistent. As you can see here, her milk production throughout her lactation is very consistent. And her friend, cow B, again, she's in the same pen at same time, same diet. She has a very inconsistent milk production. As you can see, milk production is all over the place. We found that milk consistency is a heritable trait with a heritability around 20%. We found that milk consistency is highly correlated across lactations. That means cows that tend to be very consistent in the first lactation, they are also very consistent in second lactation, and so on and so forth. We found that milk consistency and milk production are correlated with a correlation of almost 60%. That makes sense because it's a relationship between the mean and the variance. That means cows that tend to produce more, tend to have more variation. And finally, milk consistency is correlated with health and longevity. Cows that tend to produce milk in a very consistent way tend to be more healthy and tend to stay longer on a farm. So after we investigate consistency, we decided to work on resilience. In order to investigate resilience, you first need to identify a perturbation, a disturbance, and then measure the response of the cows to that perturbation. So we develop what we call a data-driven detection of perturbations using daily milk records. This is a pen. Imagine you have 80 cows in that pen, and this red line is the expected average milk production of that pen. And then when you start to investigate these dates, let's say second and third week of February, you observe that the production of that pen is lower than expected. So that is a strong suggestion that there was a perturbation in that pen. So after we detect the perturbation, we actually evaluate the response of each cow to that perturbation. Here on top, I have the 6 more resilient cows in that pen. As you can see, those cows, they have the same performance observed versus expected during these days. These cows were resilient. These cows were not affected by the perturbation. And here, I have the 6 least resilient cows. You have observed milk production in red and expected milk production in blue. You see all these cows were very susceptible to the perturbation. They have a decrease in milk production between 20, 25, 30%. So we estimate the heritability of resilience based on this decrease in milk production for different perturbations in terms of the duration from 3 days to more than 10 days, and severity, how strong was that perturbation at the pen level between 3 and more than 70%. And we observed that the heritability of the trait increases with the duration and also severity. In other words, the resilience is more expressed under challenging situations. I told you before that we investigate consistency, and now we are working on resilience. So we try to answer the question, is consistency and resilience the same trait? So here I'm showing the genetic correlations between resilience and consistency, depending on the duration and the severity of the perturbation. And we found that resilience and consistency are genetically correlated between 30, 40, and 50%. But as you can see here, the traits are different. They are correlated. That means cows that tend to be less consistent tend to be less resilient, right? But the correlations are far from one. So we should consider consistency and resilience as different traits. And in our last study, we evaluate the relationship between resilience and production. We actually quantify, we evaluate different resilient phenotypes and 3 of 5 milk production. And we observe that resilience and production are correlated. That means cows that tend to produce more milk tend to be less resilient. No surprise, but as you can see here, the genetic correlations are not strong. We are talking about genetic correlations between 10, 15, 20, 25%. So yes, high producing cows tend to be less resilient, but the genetic correlation is not as strong, and we will have room to select for both traits at the same time. I want to finish with some take-home messages. This is not new. There is a growing public concern, consumer scrutiny over dairy farming. There are concerns about animal welfare. There are concerns about the environmental impact of dairy farming. There are concerns about the use of pharmacological interventions, could be antibiotics or reproductive hormones. And I strongly believe that genetic selection is a critical tool to improve dairy sustainability. Now, I didn't have time today, but to show you this, but of course, our best selection tool is economic selection index. So we need to try to incorporate this sustainable trait like methane emissions and resilience within an economic selection index in order to improve sustainability. And of course, genomics has facilitated the selection for novel or sustainable trait. We have been working on feed efficiency for the last 10 years. We are working now with methane emissions and resilience. Maybe in the near future, we can work with estrus expression or thermoregulation. I want to finish acknowledging my team. They do all the work. They deserve all the recognition. I want to thank the data providers and the money providers. And again, thanks for your attention. Thanks for the invitation. It's a pleasure to be presenting today, and I hope you have enjoyed my presentation. Thank you very much.